we are very happy to have Hanno Sahlmann from Friedrich Alexander University Erlangen and Nuremberg. Um, he is going to tell us about hyperinvariant SU2 invariant networks and toward connecting loop quantum gravity and AdS CFT. Please.
Thank you, Machine. It's a great pleasure. In fact, thanks to all the seminar organizers for inviting me. And of course, also to everybody that's now joined. Very welcome also from my side. And thank you for being here. I appreciate it. So these networks in my title, they are very specific, highly entangled states of loop quantum gravity. And I will explain more detail what they are. But all of what I'm going to say is going to be in the context of some larger story. And the larger story is this confluence of quantum information and quantum gravity. So at the most basic level, I think one can say, well, there are some mathematical structures and some tools that are shared between the areas. But of course, it seems to go much deeper. And this being the Without Spacetime seminar, I think many of you have some feeling that spacetime on a fundamental level is something very different than what we perceive. And I guess one candidate for what could replace a classical spacetime are actually sort of notions from quantum information like entanglement and correlations and so on that then tell us about spacetime in a sense. And in this talk, I am going to report about some particular approach to quantum gravity and its intersection with quantum information. It's loop quantum gravity. And in fact, that overlap with quantum information is very interesting subject for loop quantum gravity, and many people have done work on this. And in fact, I will not be able to do justice to almost any of, or to any of that work, but let me just give a shout out to a couple of them. So for example, our chair, Mushin, has done some seminal work, and also Daniele, I saw, Daniele Oriti, has worked in this area a lot, but also many, many others. So please, if you're interested, also check out those works. I will give a few pointers later on. So to give you, to present the results that I want to present, I have to give you some context. And the context is threefold in this case. I have to say a few things about quantum information so that we are on the same page, like tensors, entanglement, etc. Then I want to give some short introduction to loop quantum gravity so that you at least get the basics. And finally, I want to recall just a few, like in broad sketches, what the AdS CFT correspondence is. And in particular, and in a little more detail, I will report on some models for this correspondence that have been studied in the last like 10 years. And that is then the context in which all of these things can go together. And I will talk about loop quantum gravity, what loop quantum gravity can do, perhaps in this context. So some basics of quantum information. By the way, interrupt whenever you have a question. I will sometimes maybe be a little fast or not go through all the details on the slide. I'm happy to elaborate or come back to it also later.
Hanno, are you sharing slides?
Yes, I am.
You are not.
Okay, so now
I can see the slide.
I'm puzzled because
I can also see them.
Oh, okay. Maybe it's my problem. Sorry, I will try to fix it.
no problem. I mean, if it's your problem, then maybe it's some other people's problems too. So, okay, but if the majority is not puzzled right now, then yeah, but then shout. Thank you. Good. So some basics of quantum information. So in what follows, much of the time we will be talking about a very seemingly simple situation, namely a multipartite quantum system. So with that, I mean a big system that's composed of subsystems. The subsystems shall all have finite dimensional Hilbert spaces like this d-dimensional Hilbert space here. And of course, rules of quantum mechanics say we use the tensor product to describe the Hilbert space of the full system. And well, in this case, we say we have n small system. The quantum information people also call this n parties. Each has local dimension d. And then we have a state space, and the pure states of this system, this big system, can be expanded in a basis with respect to a basis of the small system. And the coefficients we refer to as a tensor. And it will be very convenient to also draw these tensors. This is some calculus that goes back to Penrose and even earlier. So in that calculus, a tensor is just a blob with some legs, as many legs as you have tensor factors or parties. And things like scalar products or projectors can just be drawn in this way. Now, there's something very magical about the states of this in this tensor product Hilbert space, namely entanglement. So roughly speaking, the non-separability of states in terms of states of the little subsystems. So when they are not product states. And now, this is a very important resource for things that one can do with quantum systems. So one wants to quantify it. And for two parties and pure states, there are many measures, but they all basically say the same. We can use entanglement entropy, which you get by, so well, in this case, you only have two parties, but you can also do this for more parties. You just have to divide your parties into two groups, and then you have two subsystems, A and B. You take your state, you make the density matrix out of it, you trace out one of the two subsystems, and then you are left with another density matrix. Then you take the von Neumann entropy of that. And so evidently this entanglement entropy is maximal when the reduced density matrix, sometimes also call it the marginal of the state, with respect to A, is proportional to the identity. Yeah? Graphically, something like this. And so in general, that is with more parties, that is multipartite entanglement, and that's complicated to quantify. But everybody sort of agrees what are the champions of multipartite entanglement. Those are the so-called AME states. Stands for absolutely maximally entangled. So one can hear it from the name. They're really, really, really entangled. And what sets them apart is, or the property that defines them is a generalization precisely of this thing that if you trace out a subsystem, then you get the identity as the reduced density matrix. Namely, for those AME states, also called perfect tensors, you can trace out half of the parties or even more in any way you want. Any combination, and you will get a resulting reduced density matrix, a marginal that is proportional to the identity. And so these are a lot of conditions, and they're nonlinear and so on. And so you think, okay, can there even be solutions? And the magic is that there are, not for all local dimensions and all number of parties, but for some combinations, there are such states. And what is useful for us is that one can equivalently say, well, any tensor, you can divide its legs into two parts, And then the tensor is a map from the tensor product, or the one set of legs to the other set of legs, so from the one sub-tensor product to the other. And in the case of these perfect tensors, these maps, when they can be, namely when they go from a smaller or equal number of legs to another number of legs, then they are isometries. So they are either unitary or unitary to a subspace. Yeah? And that will be important in the following. So that brings me directly to codes, quantum codes, especially quantum error correcting codes, certainly very important for doing quantum computation. And maybe you've seen this. Here's a circuit diagram for the Shor code, like the first viable example of this. And these circuit diagrams denote unitary maps. So that's but here on the left, you only have a subspace of that Hilbert space, namely that's 0 everywhere here, and there's a non-trivial state only there. And so altogether, this thing is an isometry from this subspace onto a bigger space. And that's one way to look at codes also more abstractly. It's an isometry from some logical qubits to some physical qubits, although doesn't mean that we really want to build them, but that's the language used. And since there are more of them, there is some sort of distance between the images of the logical qubits, and so you might be robust against errors, or even be able to remove the errors. And one important thing that one can do, one can, of course, operate on the sort of one side of this isometry, but an operation here on the logical qubit can be pushed through to the sort of other side, to the code space, and just in a trivial way. And yeah, so that means that one can do the operations also on the physical things. And so these perfect tensors give very nice codes. That's one application of them. You can forget about many of the physical qubits and still reconstruct the logical one. Now, last remark, you can take tensors and contract over some of the indices, and then you get what is called a tensor network. And there are many, many forms of these, and they are good for describing various states, physical states of various systems. Yeah. And that brings me to the next topic, but perhaps I stop very briefly and ask if there are some questions so far. Good. That's not the case. Then I go on. Basics of loop quantum gravity. So, of course, it's a quantum theory of gravity. Some assumptions go in, like space-time dimension, a formulation involving gauge fields, and that sort of general covariance is very important. And so background is avoided as much as possible. So in particular, no flat background anywhere. And there are interesting consequences of this. So it's a quantum field theory of geometry. There's a discrete and combinatorial picture, so of little atoms of space, or even atoms of space-time in a sense. But of course, since one is kind of far away from this perturbative situation, it's not so easy to take a classical limit or even interpret this operationally. So this is way too technical, but just to give you an idea that there's a sort of a procedure to go from some classical formulation to some quantum theory. And the main point, or one of the important points to remember, is that is a description not in terms of the metric, but in terms of the frame. So sort of the square root of the metric. And since you can rotate frames, but that doesn't change the metric they encode, there's a local gauge invariance that is coming into play. And then there's some action besides the frame. It also depends on some connection field, some gauge field. And suffice it to say that the equations of motion of this imply that the metric encoded by the frame satisfies Einstein's equations. And yeah, so far, so good. And what you can do with this description is you can go to a Hamiltonian viewpoint. So you split space and time, space-time into space and time. Something happens to the gauge group. It gets a little smaller in this process, gets down to SU2. And you get two canonically conjugate fields E and A. And again, I don't want to go into details, but you can think of them as some electric field and some vector potential. In fact, they are, for all practical purposes on a kinematical level, they are like the canonical fields for SU2 Yang-Mills theory. So gravity sits inside that Yang-Mills theory phase space in this formulation. And the dynamics sits in some constraints, like the Gauss law for electrodynamics. That's one of the constraints, but then there are two more. But I will not talk too much about this dynamics. Again, the whole thing, if you take all the equations that you have, is equivalent to Einstein equations. So one important thing, if you want to talk about quantum theories, to think what are the quantities that make sense even in the quantum theory. And for various reasons, the choice in loop quantum gravity is to not take this vector potential, this gauge field directly, A, but take the parallel transport that it induces. And so these parallel transporters along some path in your spatial manifold, they're called holonomies. They're group valued, and under what physicists call a gauge transformation, they change in a very simple way. They just transform at their endpoint, so at their target, and at their beginning, at their source. Therefore, in particular, if you take such a holonomy around a loop, then it doesn't change under gauge transformations, or the trace of the holonomy around the loop. So for the electric-like field, you can also think of operators that should be well-defined or that turn out to be well-defined. And those are, for example, spatial area and volume. So the spatial geometry, they are aspects of this electric field with spatial volume having to do with the determinant of this electric field and the area with its length. Now, the states of this theory, they arise from a vacuum by sort of action with holonomy operators. So they are like creation operators. They create excitations. So these excitations are line-like because the holonomies are. And they are excitations of geometry, as you can probe. Yeah. So for example, you can create such an excitation out of the vacuum, and then you can probe it with an area operator. And if this excitation hits the surface through which you measure the area, well, in any case, so this state turns out to be an eigenstate of area, and if the loop hits the surface, then it has a non-zero eigenvalue of this form. Of course, you can create more complicated states when you keep on acting with these holonomy operators. Or I didn't say it. So in these holonomy operators, you can also use representations of. So these are SU2 elements. So you use irreducible representations of this to create different excitations, and they change the area and so on. And at the end of the day, there's a basis for the states that you create. It's called the spin network basis, and it has this form that it is labeled by a sorry, I messed up here. It is labeled by a graph. So, and then for each edge of the graph, an irreducible representation. And for each vertex, and that is very important, an invariant tensor. So there's a tensor in the sense that we had at the beginning. It's not arbitrary, but it is invariant under the action of the SU2 group, the diagonal action of this SU2 group on each of the legs of this tensor. And that's because of gauge invariance. Okay, so in that sense, you already see basis states are tensor networks. I already said area quantized and so on. One can say a little bit more about this. Volume also quantized, and the volume sits at the vertices of this network. Yeah, and in fact, one can, in a certain quite justified way, think of an n-valent vertex as a little quantized polyhedron with n faces. And so we build up this quantum geometry from these polyhedra. And well, you can also couple matter. Particularly pretty are the fermions. They sit at open ends of the spin networks or on vertices more generally. And they have to couple to the gravitational field because they also transform under the gauge transformation. So they are very strongly coupled to the gravitational field already at the kinematical level. And their spins also influence the gravitational field and so on. Now, there is also dynamics. And I think right now I'm just going to almost skip this, just to say, ultimately one shouldn't forget this. There are quantum Einstein equations, and some of them say basically that it doesn't, for these networks, it doesn't matter where exactly these edges and vertices are. The geometry is in that state, not how the loop looks like. And some of them really sort of say something about correlations in the linear combinations of these networks, like what makes them satisfy the equations, specifically the Hamiltonian constraint. And there's some very beautiful picture in which one can so one is interested in this kernel of the Hamiltonian constraint, and there's a very nice expansion by Rovelli and Reisenberger, formal expansion of this, and the terms can be interpreted as some sort of Feynman diagrams of these spin networks, where sort of you have only Feynman diagrams, only one dimension higher, where these networks undergo changes that are described by a two complex that is in between them. Yeah, and that leads to some more covariant picture of loop quantum gravity, so called the spin foam picture. And very nicely, you can also get there directly from the discretized path integral. But I don't want to talk about that more. I want to go back to the observation we had that a spin network or superposition of spin networks is on the one hand associated to a quantum geometry, as I sort of try to depict here and also explain. But on the other hand, it's a tensor network. Yeah, so you have these invariant tensors at the vertices. You have the holonomies on the edges, which are unitary tensors, if you like. And you can even say the fermions are little qubits, yeah, that are at the ends of your network. So of course, that makes it very natural to study the entanglement in these networks in various ways. And as I said, there has been a lot of work both in the context of black hole entropy and also more generally in states of this space. And but what is relevant for this talk is on the one hand, sort of looking at holographic aspects of this entanglement, so bulk boundary relations, and both Daniele and also Mushin have done very interesting work on this. And also what I'm going to present is in that context. So then again, I take a little breather and ask you if there are questions.
I don't have a question so much as a comment. So, I mean, even though like it is quite physically obvious that tensor networks and spin networks are in a one-to-one correspondence, for the longest time, there was very strong pushback from many people whenever I would try to raise this. And so, you know, even though Mushin had written this paper that you just mentioned in 2017 itself, but even then he said that they're not really tensor networks for some reason. I forget exactly why. But one can show quite explicitly that if you write down, the expression for a spin network amplitude, it's exactly the same as that for a tensor network state.
Thank you for the comment, Deepak, and I'm sorry that you had this, you felt there was this pushback. So at least, so I can't speak, of course, for the past, but I think presently this is, of course, taken quite seriously. I hope. Thank you. Okay. So then AdS CFT. So very briefly, AdS spacetime. I've brought you two. So first of all, AdS comes in dimension 2 and higher. It's a solution of Einstein's equations of the respective dimension, no matter, but a negative cosmological constant. And it's very symmetric, maximally symmetric, in fact. And one fact about AdS is that you can embed it into Minkowski space in a very nice way. He has shown for two-dimensional AdS space, but this works similarly for higher dimensional space. So you see the time direction here goes up and then down here and around. So in this in this form, AdS has closed time-like curves, but you can unroll it and then avoid that problem. What you can see very nicely at this embedding is that if you slice it at constant time, here, for example, then what you get is a hyperboloid. Yeah, so your mass shell, if you like. And in fact, that's also that generalizes to higher dimensions. So you can slice AdS in a way that the spatial slices are hyperbolic spaces. And so that's used in the picture below here. But so here it's indicated that these are sort of hyperbolic spaces. Something else has happened here. There has been a conformal transformation so that the spatial infinity here has moved to finite distance. And that is important because AdS CFT deals with the correspondence between fields inside AdS and fields on the boundary on this asymptotic boundary of AdS. And from various angles, it has been seen that quantum gravity of AdS spacetime or near AdS spacetime or for spacetimes that are asymptotically AdS are somewhat special, and this AdS CFT is one example for this. So I already said is a relation between bulk and boundary, and most famous is this work by Maldacena that started this on a particular type of string theory on an AdS background, which then is mapped under this AdS CFT to a super Yang-Mills theory on the boundary. But in fact, like lately, we are talking a lot about, sort of bulk fields and their relation to boundary fields and so on, both asymptotically, but also at finite distance. And so one should not be surprised that there is sort of many different aspects of this, many different situations in which interesting things can be done. So many different cases have been considered, different dimensions, different field content, and so on. At least in the original incarnation, it's supposed to be a holographic relation. So although the boundary is one dimension less, it's still supposed to be sort of equivalent. The boundary theory is equivalent to the bulk theory in the sense that it has all the information about the boundary, the bulk physics. And so again, so maybe I should emphasize this. So this is a huge sort of area that has been probed and so on in many directions. And I'm just now picking two aspects of this. And one aspect of this correspondence is what is called the Ryu-Takayanagi conjecture. After, well, Ryu and Takayanagi, who in 2006 did some calculation in very low dimension, where they showed that you consider the conformal field theory on the boundary. And again, like at the very beginning of my talk, you divide the boundary into two parts, A and B, two subsystems. And you ask, what is the entanglement between A and B? And then it turns out that entanglement entropy is given by, in this drawing here, the boundary is two-dimensional, and then the entanglement entropy is given again by an area of a minimal surface that goes into the bulk, but has the same boundary as A and B. And that is one instance where you see that from the conformal field theory on the boundary, you can learn something about the bulk. Yeah, you learn about the minimal surfaces and their areas, for example. Yeah, and so of course, in some cases you can maybe prove something, but in other cases it's a conjecture. And another aspect of this is that if you again pick some sub region A of the boundary, then you can do operations there, and then you expect that because of holography, from that information, from these operations here, you can sort of recover physics or do physics with certain points in the bulk. And you consider the causal relations between all of this, and then you come to the conclusion that this should be possible given some boundary region A in what is called the causal wedge of the bulk. And so these are, I won't define. But one thing that from this drawing, you can probably guess, is that in fact, given a point, there are many different boundary regions A, such that the point is in the causal cone. And so, in fact, this information about the physics at X is, in a sense, holographically encoded in the boundary theory, because you can recover it from operations here in A, but you can also, there's a different cone that also contains this X with respect to a different part of the boundary. You can also recover it from operations there. And so that is that reminds one perhaps of the codes that we talked about. And in fact, this motivated people to look into this. The idea is to make a model for this in which the boundary state, so a very simple model, not field theoretical, but finite dimensional model, which the bulk is described by, and the boundary, if you like, by a tensor network. And to sort of capture the geometry of AdS, or the hyperbolic spatial slice, you say that this tensor network is dual to some regular cellular decomposition of this space, as indicated here in this drawing. And then you say that the geometry in the bulk is like, given by the number of, the volume is given by counting vertices in that area, and the surfaces are given by counting intersections with legs of the tensor network, and so on. And very specifically, in 2015, actually two such tensor network models were proposed by Pastawski et al. They are models for AdS CFT in 2+1 dimension. And they are both based on the same tensor, a perfect tensor in both cases. And once the tensor, so it's a tensor with 6 legs. And once all the legs in the bulk are connected to other tensors like this, and so on, but one doesn't maybe go to infinite extent, but one just stops at some point, and then one has a boundary here, and then one has open legs at the boundary. Or one uses that same tensor, but one only connects 5 of the 6 legs in the bulk, and one leg is left dangling. That's some kind of bulk states. Yeah. So then you have non-trivial Hilbert space associated to the bulk. And now you can, they show that in this model, Ryu Takayanagi is a theorem in the sense that you find that if you again divide the boundary into 2 subsystems, then the entanglement between the two is given by the length of the geodesic with the same boundary. And length here is just counting the intersections with tensor legs. And this you can show, we can discuss it maybe later. This is intimately connected to these isometry properties of these perfect tensors. And they also pointed out that in this model where you have bulk states, also bulk qubits, this kind of tensor network is actually a code that encodes the bulk qubits into the boundary qubits. And it is holographic in the sense that, for example, you can have an operation on this bulk qubit, but since this is a perfect tensor, in particular, you can have an isometry from this leg, and the bulk qubit to 3 other legs in this way, and then you can push that operation through, indicated by these arrows. And so this operation on this bulk qubit can also be done as an operation on these other bulk qubits, and one can continue to do this. And so ultimately one finds that that one can realize this operation on a lot of the on qubits on the boundary, and this is exactly the discrete analog of this sort of wedge, I mean, reconstruction of the bulk physics from the boundary here. And you can see that you can do this in different directions. So again, this qubit is not just represented here, but it's also represented here, and operations on it can also be represented by operations on this other part of the boundary, because everything is very tightly entangled. So now I see I have to speed up a little bit. So not everything is perfect with these models, however. So one thing that people considered is the correlators on the boundary. And if you think that should be a CFT, then you have an expectation that they are roughly polynomial with distance on the boundary. And for these models, this is not the case. They are decaying practically. I mean, they're decaying less because these tensors are too perfect in a sense. But this led to some development of many more models. For example, models that use random tensors, because you can approach, I mean, you can, as a matter of this concentration of measure, when you have high local dimension, then your random tensors will become quite entangled. And so models with these random tensors maybe don't have perfect entanglement, but that is better to actually reproduce the boundary correlators. There's a whole family of models as a generalization. They are called hyperinvariant tensor networks, and I will say something more in a moment about these. Of course, you can also consider other tensors, like constructed in a very smart way, that have good properties. But with all of this, maybe two things are not addressed. And the one is that in the bulk, you don't really have quantum geometry. You have just counting of things. And all in all, this is relatively ad hoc. It doesn't come from anything. And so that brings me to the hyperinvariant tensor networks from loop quantum gravity. Questions up to now? Okay, then I keep on going. So, well, the first idea is, I mean, the obvious idea is to use, or relatively obvious idea is to use tensor networks that are states of loop quantum gravity. And the first question one faces is, are there SU2 invariant perfect tensors? And this is a question that was asked by Mushin and his collaborators in 2016. And so it's a very nice mathematical question. And well, it has some chance, because you look at the 3-valent SU2 invariant tensors, and they are all perfect. And then what they did is they looked at the 4-valent ones, and this was already quite a calculation, and they found that none were perfect. unfortunately. And so this was where it stood for a while, and then at some point I got involved together with a student or former student, Refik, and we showed that in fact if you go to higher valence, so the hope was maybe the odd valence would be working and even valence would not, but any valence for spin 1/2, it doesn't work. There are no perfect tensors. And independently of us, also Ottfried Kühne and Finn Otto showed the same thing. And then in this situation, we got together and actually sort of unfortunately killed the rest of the cases. So there's a lemma that says that if you have a tensor for more than 3 parties that is invariant under some non-trivial action of not even SU2 but already U1 is sufficient, then there's at least one two-party marginal that is not equal to the identity or proportional to the identity. And so these perfectness and this additional symmetry are sort of impossible to combine. And so from that, various no-go statements follow. In particular, there are no perfect SU2 intertwiners for more than 3 legs. So what can be done? Well, a lot can be done. So one example, but not the only example, is by Mushin and his collaborator in 2016. They considered 4-dimensional loop quantum gravity, and their idea was that well, maybe this Ryu Takayanagi formula should not hold in sort of on the most microscopic level, but in some sort of semi-classical regime where one considers sort of some coarse graining of the spin network or the loop quantum gravity state. They also used random tensors, and in this setting they found a Ryu Takayanagi formula, and you can see now so that states that this entanglement entropy on the boundary is proportional to sort of area of a minimal surface in the bulk. And there are specific constants here. So you see now it pays that you have contact to quantum gravity. You can make very specific statements. And similar, but also different settings were also considered by Daniele and his collaborators. And so in this, I mean, for example, for random tensors and also in this kind of semi-classical regime, in fact, statements can be made. And what in the last sort of 5 minutes, what I want to tell you is that there's a complementary approach that we have been pursuing. Namely, there's this class of tensor networks that will give you these entanglement properties called hyperinvariant tensor networks. They are built now not just from one tensor, but from 2 tensors, A and B. A can have arbitrary valence, but they have to satisfy certain isometry conditions. They have to also, the A has to be invariant under cyclic permutations. And so here's one isometry condition. So the 1-to-many marginal of A has to be maximally mixed. B has to be unitary. And this combination of A and B also, this combination of A and B has to be an isometry. And if you build a network from these tensors on a tessellation of the hyperbolic plane, then you automatically get Ryu Takayanagi. That's what Evanly showed. And so then one question is, can one get these kind of networks from loop quantum gravity? And well, so we have to step back for a second, because right now we are talking about AdS 3, three-dimensional AdS. So we are talking about 3D gravity. One can also do this with loop quantum gravity methods. Many things work, but with one dimension down. One thing that is a little different is the gauge group. So for Lorentz signature, you get SU11, and this comes with technical difficulties. So what one can do is one can use Euclidean signature instead, and then one is back to SU2 and the intuition from 4D loop quantum gravity. There are also geometric operators like length in that case and area, intrinsic volume. And so going with this, we found that there are indeed these hyperinvariant and SU2 invariant tensors, tensor network, called HITS, together with Refik and Utfried and Finn. And right, so here are some examples. So what is important is two things. They come from sharing Bell pairs of qubits, and in particular on the legs of the tensor A, for example, you don't just want one qubit, but you want several of them. So in other words, on the legs of the tensor, the representations of SU2 are not irreducible. That means these things are complicated linear combinations of spin networks, and that actually enables the kind of entanglement that is needed. And so here are some examples. So you can just star-wise connect these qubits. B can be an arbitrary unitary. You can do more complicated things like this. There are further sequences of states that work, and there's also a tensor product construction to build more complicated ones from these elementary ones. So there's quite a bit to play with. Although they come from sharing qubits, they are still highly entangled by various measures of multi-partite entanglement. But what is more important for me is that now they have a genuine quantum geometry in the bulk. So we have so the geodesics here, or more generally the lines in the bulk, they have a length that we can take an expectation value of, and because of the particulars of loop quantum gravity, it turns out that in fact the expectation value for the length is proportional to the intersection number, but there is some constant that's coming from the particular tensors. And well, you can say that, okay, so all you got from this is this. I mean, this is good because it's compatible with the picture that is already there. But of course, well, did you just gain a constant? But well, for example, one also has fluctuations. So lengths are fluctuating. One can calculate the fluctuations. And while I don't have any particular expectations about this, it looks quite healthy in the sense that relative fluctuations are suppressed. So if you have a large geodesic or something like this, then it fluctuates, its length fluctuates. I mean, the relative fluctuations are small. These calculations are not so easy because precisely these things are, they contain all sorts of spin networks. So one has to find tricks to do this. I will be short here. So area and so intrinsic volume works the same way, also proportional to counting the number of tensors that are in a given region. But again, there are fluctuations, and again, there are some constants that one can work out. There is angles, and from the angles we can get curvature, and we find that indeed this particular example that we studied is a quantum geometry with negative curvature. We can also calculate boundary correlators, and they are non-trivial, but to get this kind of scaling behavior as one would have in CFT, if one makes the boundary bigger, then one also has to scale the local dimension and the number of qubits per leg appropriately. So it's not like the most natural outcome here. Let me finish. So I hope you do understand that these holographic tensor networks are interesting to study this bigger duality, both from the quantum gravity side, but also they give interesting codes for quantum information. And so quantum gravity is this quantum theory of geometry, quantum field theory of geometry, and its kinematical states are tensor networks, and so quantum geometry and quantum information go hand in hand. I have shown you these highly entangled states that have holographic properties, and together with these other results from Mushin, Daniele, and others, one sees that one can actually have holographic tensor networks from first principles, yeah, in a sense, because they come out of this theory of quantum gravity. But there are lots of questions, of course, with respect to these particular states. I would like to go to physical signature and dimension. I also want to consider codes and holography in that sense. And important point, the dynamics, the Hamiltonian constraint, or potentially even more other aspects. And finally, this of course can be generalized to questions of what are the correlations in states that approximate other geometries like black holes and so on. Of course, some of these have already been studied to an extent, but there are many open questions. So with that, I thank you very much, and I'm sorry I ran sort of over time. Thank you for your attention and for your patience.
Okay, thank you. Yes, I see many people clapping. Thanks for the nice talk. Very, very clear, very comprehensive. Is there any question? Daniel.
Yeah, thanks, Hanno, for the talk. Very brief because I have to go, unfortunately. I'll be happy to discuss more when we meet, hopefully soon. So one question is whether anywhere in this construction with hyperinvariant tensors, you need to impose something like AdS boundary conditions, or if there is any restriction that has to do with directly with the geometry encoded in the networks that will be required to have proper holographic behavior.
Thank you. That's a very good question.
And the second question, so that I make the two questions and then I just let you answer, is whether you already started in any way looking at the dynamics in the 3D case, like checking what happens with the flatness condition Because that seems doable. I mean, the 4D is much more involved, but the 3D should be okay to some extent.
Thank you. Thank you. So I'll try to be short. With respect to the networks, there is some trace of this hyperbolic geometry. So it is relevant that the graph has this this connectivity structure that mirrors the geometry. Otherwise, you get I mean, when you try to use the isometries to move, to sort of push your cut between A and B into the bulk and do this reasoning, you run into problems. So there is there's something encoded, but on the boundary itself, there is nothing. But you can already see this if you look at the codes. Then you have to have more boundary bits than bulk bits, and so that's one aspect where the geometry, this hyperbolic geometry, comes in. If I would just take a square lattice or something like this, then it wouldn't work. Then I would have too many bulk things. As for your second question, yeah, it's you're right. It's doable in 3D, and we are looking into this. That would be very interesting to know regarding the dynamics, specifically if these kind of things in some sense satisfy the constraint for 3D with negative cosmological constant. Thank you.
Okay, Richard.
Really nice talk. I just wanted to ask a little bit about the quantum codes perspective on this stuff. So maybe I missed it a little bit, but I wanted to be clear on what the advantage of your approach to these particular spin networks offers in comparison to just having random spin networks. If you have a random tensor network and okay, you've restricted yourself to spin 0, this thing is still pretty robust. It's robust against, I think, most of the errors you talked about, plus maybe Pauli noise of, it depends how big they are, but they could be quite high weight as well. Why go to the effort of this particular structure when you could just randomly spam spin networks?
Okay, that's a fair point, and I guess it's a matter of perspective. So perhaps these two things gives you different insights. So it's a very nice result that in some sense there's a robust holography or something like this when it comes to loop quantum gravity. Under certain assumptions, you will get this. On the other hand, I don't know. I do believe that, for example, when it comes to solving the constraint or something like this, then we might have to really talk about particular states and particular tensors and so on and so forth. And perhaps there are special ones. There are ones that are very, suited for a certain geometry. And so it's interesting to know them. But indeed, it is reassuring to see that there is a certain genericness in a limit, and perhaps this is already all one needs. But these are very particular states with special properties. You could speculate that they are important somehow, but they might not be.
Okay, thank you.
I have a few questions. So first one is in your last part about hyperinvariant tensor networks. So I see the area law, the RT formula that you reproduce, it's like it's proportional to intersection number. So it's not the geometrical area. It's like more like topological area from loop quantum gravity perspective. Yeah, have you thought about doing something like cross graining to get the geometrical area law, the LQG area?
Okay.
Yeah, similar calculation.
So shall I answer already?
Yeah, please.
So I agree and disagree. So I agree that it turns out this length in our case is proportional. So it's added. Let's say it's additive in the intersections. Yeah, it's additive in the intersections, but that doesn't mean that it's not. I mean, in fact, it is the expectation value of the length operator just has this property. It comes out like this from loop quantum gravity. So this is the loop quantum gravity area or loop quantum gravity length. Of course, one can go further and one can look at linear combinations. Maybe that's what you mean. Linear combinations of different tensor networks, yeah, with different valences or different something. And then, of course, you would have contributions that, for each of them, there would be terms. For each intersection, there would be a term and so on and so forth. So maybe that's what you mean.
Yeah. Yes. So yeah. Okay. So yeah, I'm thinking maybe you can do something similar like black hole entropy computation that it relates to the physical area of the of a large surface, something like that. Yeah.
I mean, I see. So then you pose let's say, a constraint on the area. You say it should be something, and then you look at all tensor networks that have that particular area, and then in particular ones that have arbitrary number of intersections with the surface. That is certainly possible.
Right, and in particular, those tensors are those states are maximally entangled. So all the states are equally distributed. So it's will be analog of microcanonical ensemble because all the states has same weight. Okay. Another question is you mentioned fermion at earlier part of the talk, and so is there any result relating fermions to tensor networks in loop quantum gravity and entanglement?
Okay, so maybe I can say a few things. So okay, so if I'm in 4D gravity, then these fermions are coupled in an SU2 invariant way, and then the same sort of no-go theorems apply because, yeah, I mean, then you might have problems having code, sort of a code that connects these fermions in the bulk to stuff in the boundary. But in okay, so what else should I say to tensor networks? Well, I mean, in a sense, you can say like these bulk qubits. They could be geometric degrees of freedom, or they could be fermions that are coupling to this. And of course, but this is probably not what you. This probably what you already know is that, of course, the fermion locally deforms the geometry and will sort of change the volume spectrum and so on and so forth locally.
Okay.
Okay. Sorry, I'm a little bit slow. You can also ask what is the entanglement between the sort of among fermions. You can have a state with fermions, and then you can trace out gravity, and the result is a little bit surprising in that it turns out they are not at all entangled with each other. It's basically because monogamy of entanglement that the fermions are super strongly entangled with the local geometry, but then they are not entangled at all with the faraway geometry. But you can, if you ask the question in a little bit more subtle way, then you can actually produce things like a Bell pair of fermions. So then, in fact, it's you have to sort of distinguish I mean, you have to measure the spin state of the fermion relative to some geometry, relative to some surface or something like this, and then there's a loop quantum gravity state that would correspond to a Bell state of two fermions that are far away. There's some work that I did with some student.
Okay, thank you. Next question, Josh.
Hi, thank you very much. I was just wondering about the case where you said you recovered the CFT correlator in I think it was like a large bond dimension limit. The question is should I think of that as a continuum limit? And also you said it's perhaps not what you expect and can you expand on why you would not
expand on
expect
this?
that?
I haven't really. I mean, I would say that I mean, I can. What I can do is I can say I want this and that correlator behavior on the boundary, and then then that gives me sort of information about what you said, the bond dimension and some other parameters of this network. And so if I scale, if I really make the boundary go far away, in fact, then I cannot leave these things constant, but they have to scale. Perhaps one can have different networks that behave in a more complicated way, so that one doesn't have to have the scaling necessarily, or it is something that, well, for example, Mushin also has in his work, that there is some sort of semi-classical limit or something like this that is has to do with this large bond dimension and large number of legs. I don't know.
Great. Thank you.
All right. Is there any other question or comment? Okay, that seems not the case. Yeah, then let's thank Hanno again for the nice talk.
Thank you guys for attention and for the good questions. Thank you.
Thank you, Hanno.
Thank you.